If you're building robots, or really any project that needs controlled linear movement, you absolutely need to understand how linear actuators work. Get it wrong, and you're looking at a weak design, or worse, a broken mechanism and a trip to the parts bin. But get it right, and you can create some seriously powerful and precise motion. In this video, I'm going to show you exactly how a common type of linear actuator works and how it translates that motor rotation into a strong linear push and pull force. Understanding this is going to make your life a whole lot easier when you're designing and building, and it's a critical skill for anyone serious about robotics, automation, or even just want to do some cool do-it-yourself projects. I'm Brogan Pratt, and I've been teaching robotics, design, and technology for over 10 years. And trust me, I've seen countless projects succeed or fail based on how well components like these actuators are understood and implemented. So here's what we're going to do. We're going to use this actuator as an example, and we'll look at its core components. Look at the frame, the extension, the lead screw, and how the motor and gearing drive everything. And critically, we'll cover why managing your travel limits is non-negotiable with many actuator kits to prevent that damage. Now let's head over to the workbench and take a closer look. Okay, so here it is, all assembled. This is a great example to understand the fundamental principles. Let's break this thing down to see how it actually functions. First, we've got the main body, our U channel. Sometimes it's called a C channel because it looks like the letter U or it looks like the letter C. This U channel provides that rigid framework for the entire actuator and keeps it strong, keeps everything aligned. So many actuators are going to have a similar outer casing. It's not necessary, but it does really help protect your lead screw. This part here is the part that actually moves in and out. That's our aluminum extrusion piece, sometimes called the extension. This is what provides your actual linear motion, or that push and pull. And you can see how it slides in and out of this outer channel as I rotate this motor around. So you can see as I rotate this motor, this thing slides up and down quite smoothly. Now, supporting this rail internally are two different acetal plates. And these acetal plates right here, these acetal plates act as a low friction guide between the outer channel and that moving rail. In this particular setup, these plates can be mounted any length along this channel. That allows you to change the overall length of this actuator. So you can use a different piece of aluminum extrusion. You could have it shorter. You could even have it longer. And by doing that, it allows you to change the overall extension length of the actuator. This also allows you to say how much lateral or sideways support this piece of aluminum extrusion actually gets. More support that you have, the less wobble you're going to have on this system. And that's really important when it comes to precision. So how does it all actually move? It all starts with your motor. I currently have an 1150 RPM 12-volt planetary gear motor attached. This is a pretty common motor used in FTC robotics. And it's attached directly to the motor shaft. I have a 60-tooth gear. This gear meshes with another 60-tooth gear, which is mounted on our lead screw. Hidden behind that piece of aluminum extrusion is our lead screw. Since both our gears are 60-tooth, that means we effectively have a 1-to-1 gear ratio between the motor's output and the lead screw itself. That means for each one rotation of the motor, it's going to rotate that lead screw one rotation as well. So other actuators might have different gearing or direct drive, but the principle of converting that rotational movement to linear movement is key. The lead screw is really the heart of any linear motion system. As it rotates, a threaded nut, which is fixed to that piece of aluminum extrusion, travels up and down that linear screw. And this is what converts that rotational motion from the motor into that linear push or pull of the actuator. It's a simple slope, but it's a very effective mechanism that's common in many linear actuators. And with this particular motor and this 2mm pitch of the lead screw, this unit can produce over 22 kilograms of thrust, and that is a serious amount of force. And it's pretty quick too. With no load, it can extend fully in about 1.3 seconds. Now, this is super important. You cannot run any linear actuator past its mechanical endpoints. So past this point here or past this point here. If this rail tries to extend too far or retract too far, you're going to damage something. You could strip the threads in this lead screw, you could break the mounts themselves, or you could burn out your motor. And this applies to virtually all linear actuators. Some linear actuators have built-in limit switches or other sensors that automatically stop the motor at their endpoints of travel. However, a lot of different kits sometimes don't include some to be able to do that in order to keep it simple or less expensive. This means that responsibility is often on you to prevent that overrun or going past your endpoints. A common way to do this is by using a motor with a motor encoder. These motors themselves have encoders built into them. Encoder tells the control system exactly how much the motor has turned or rotated. And with that information, you can program software limits or endpoints into your code. Your program needs to know that safe travel range for the actuator, stop the motor before it hits those physical limits. For a lot of applications, this is not really optional. It's essential for your reliable and long-term operation. So to recap, we've got a sturdy frame, we've got that aluminum extrusion extension rail, we've got a motor that is driving our lead screw, and that lead screw is what converts that rotational motion out into linear motion. And critically, for a lot of different actuators like this one, you need to have a way to manage your travel limits, often with an encoder, with programmed endpoints, or limit switches at either ends to be able to prevent that damage. Understanding how these components work together, especially the role of the lead screw and the importance of managing those travel limits, is key to successfully using linear actuators in your robotics projects, automations, or custom builds. It'll save you a lot of headaches and broken parts down the line. Hopefully, this gave you a much clearer picture of what's happening inside of this type of linear actuator. I put a lot of time and effort into creating these videos, trying to break down complex topics into something understandable and useful. So if you found value in this, the best way to support this channel is to help me make more content like this, is to hit that like button. And if you haven't already, please consider subscribing. It really does make a huge difference. If you have any questions or have suggestions for future videos, let me know down in the comments below. And best of luck on your next project.